Hello and welcome to Section 2, Constraint-based algorithms. Back to our COVID example, assume that we can somehow extract a number of conditional independencies that we saw in Chapter 1 from the data set. The question is, how can I systematically obtain the p-map for the underlying distribution of these variables? Now, to answer this question, I can narrow it down to the following question. When does a link exist or it does not exist between two variables? What is the implication of it? It appears that the non-existence of a link implies some conditional independence in the graph. For example, in this graph, there is no link between x and y. And we can see that if we condition x and y on these red nodes, which are the parents of x, then the two will become independent. I can try to generalize this observation in the following lemma. In general, if I have a p-map for my distribution, then if there is no link between x and y, then definitely the two of them will become independent if I condition them on either the parents of x or the parents of y. One of them should do the job. And the opposite also holds. If two nodes become independent on the parents of the first or the parents of the second, then definitely there shouldn't be a link between them in the p-map. So it's also implying that a link between two nodes, then you can never make them independent, no matter you condition them on what. Okay, so this observation is quite helpful in building an algorithm to obtain the skeleton of the p-map. How? Here we go. First, I will build a completely connected undirected graph. I'll call it H. And then I will repeatedly remove the edge between any pair of nodes x and y that can be independent if they're conditioned on either the neighbors of x or the neighbors of y, or a subset of them. This is what we learned from the lemma. So it means to remove the edge xy if x and y are independent condition on some u, where u is a subset of the neighbors of x or the neighbors of y. If I do this repeatedly until there's no other edge that I can remove, then the final graph will be the skeleton of the p-map. Now note that u here is potentially either the parents of x or the parents of y in the previous lemma, okay, because it's making the two of them independent. And in order to speed up this algorithm, what we can do is to check u from small subsets to larger ones. So first I will check if x and y are just independent, not necessarily conditioned on anything. Then I will check if they are independent condition on just one other variable, and so on. Okay, and if one of them work, then I don't need to check the larger superset. Let's see it in practice. Back to our initial example in the lecture. We want to construct the p-map for all of these variables. I'm limiting it to the following 6. The first step was to construct the fully connected network H. After that, I need to see if any of the two variables will become independent from each other. And if I check, I see that m and d are actually independent. If I go back to the initial table, you see here I have m and d in the first listed conditional independencies. So I want to use that. And that implies that the u I'm interested in will be an empty set. Remember, we said we start from small u's, like the empty set, and then u of size 1, and so on. We will increase it. So this means that there shouldn't be a link between mask and social distancing. I will remove it. But then after that, if you go back to the list, you see that we don't have any other marginal independence. So I will look for conditional independencies where the size of u is 1. One of them is this one. I have that f is independent of m, d, b, v condition on c. Now that means that all of these links should be removed. f2 v, f2 b, f2 d, and f2 m. Okay. So after doing that, what else do I have? Well, I can see that also V is independent of MDC condition on B, and that means again that all of these links V to MDC, they should be removed. Okay. And do I have anything else? Well, yes, I can also see that B condition on C is independent of M and D, so I can remove these two nodes, these two links. And you can check that we cannot conclude anything further from here. Okay, so that's all that I will have, and this will be my skeleton. Now, the question is how to determine the direction of the edges. Well, I have the following proposition. If I have a P-map and an immorality in that P-map, to recall, an immorality is a triple XZY where X and Y are pointing to Z and there's no link between the parents X and Y. So a P-map and immorality, then X and Y will never become independent conditioned on U where U contains Z. So anything, conditioned on anything that contains the child node Z, it's impossible for them to become independent. So it's basically a V structure. We're conditioning on the child. We knew that this will be an active trail, but recall that this doesn't necessarily imply that the original distribution also is like X and Y there are independent. It just means that the graph does not imply it. Here we can make that conclusion because we're assuming it's a P-map. Okay? So anyways, this means that if Z in the previous part of the algorithm belongs to U, then it must not form a V structure with X and Y, because otherwise this wouldn't hold. Now I also have kind of the opposite. If I have a P-map and XZY are a triple that X and Y are not connected, this time if I don't have the immorality, then whenever X and Y are independent condition on some set U, then definitely U contains Z. Okay? Because otherwise it will be an active trail. This part is easy to see. So this means that if Z does not belong to the U in the previous algorithm, it must form a V structure with X and Y. Okay? See it in practice. I had this graph. Now I want to take the second step and try to direct the links. Well, for each connected triple XZY where X and Y are not connected, then we know that if Z does not belong to the U that made X and Y conditionally independent, that's why I'm putting X and Y in gray here, then we will add the directions X, Z, Y. We'll make it a V structure. So I need to check for every triple that can be potentially an immorality and see if I should direct them so that they become an immorality or not. Here, for example, I see MCD. Okay, this satisfies the conditions stated here. Now, I want to see how should I direct them. Well, I see that C here does not belong to the set U that made M and D independent. If you recall, the U that made them independent was an empty set. C here does not belong to that, meaning that it is not a parent, a potential parent for them. So it should be a child. Therefore, following what we said here, we should make a V structure in this case. Now, what about the other ones? For example, what about the case with DCB? So here, DCB, should I make it also a V structure? Well, in this case, we see that C belongs to actually the to the set that made them independent. Okay, actually, it was the only variable that was conditioned on. So here, when such a case happens, then we should basically do nothing. We shouldn't make a V structure. We shouldn't necessarily do the opposite and make, for example, C to be in the opposite direction. Okay. Now, what about DCF? So DCF. In this case, also we see that they became independent condition on C, and C belongs to the U that made them independent. So again, nothing we should do here. F, B, C, same story. We have here F, C, B, and I shouldn't do anything, and also C, B, V. C, B, V. Okay, so I cannot make any directions here. I know that they shouldn't form a V structure. I will keep that in mind. Now, what should I do with the rest of the graph? Well, we do it in a way, we direct the remaining edges in a way that avoids directed cycles, because it should be at the end of the day a DAG, directed acyclic graph. And also I should not create new immoralities, because all the ones that should have been created were done in the previous step. Okay, we can do this, or we can also use the following three rules. Rule 1 is whenever we see something like this, I should then direct Y and Z in this way. Obviously, because otherwise, if I do it in the opposite way, then I'm creating an immorality. Now, another rule is this. If I have X, Y, Z, then I should direct X to Z, because if I do it in the opposite way, I'm making a cycle. And the final rule is that if I have such four nodes, Y1 and Y2 pointing to Z, then I should point X to Z. Okay? If I do it in the opposite way, Z to X, then I should have Y1 being pointing to X, because otherwise if X is pointing to Y1, then I will have a cycle here. And same story here. So both Y1 and Y2 should be linking to X. Okay? Now, by doing this, I made an immorality, because I have Y1, Y2 pointing to X and no link between Y1 and Y2. So I should avoid this, and that's why I should make X pointing to a Z. So either use these three rules, or just use what we said here, avoid cycles and new immoralities. So back to our graph, I want to see if I can decide on the direction of these links. For example, B, C, D. If I make the link from B to C, then I will have a new immorality here, B, C, D. Okay, so I need to make C being pointing to B, like this. And for F and C, if I make F pointing to C, then D, CF, or MCF, they will be a new immorality. So C should be pointing to F. What about here? V to B. Well, if V points to B, then again I will have an immorality, so I should avoid it by making B pointing to V. In this case, I ended up all of the links, the directions of the links being determined. That's obviously not the case. We know that we have I equivalent classes, and we will see another example soon. To summarize, discovering the class PDAG of a P-map of a distribution. The algorithm was as follows. We first would find the skeleton of the PDAG. Then we would find the immoralities. That the idea was that for each connected triple XZY, where X and Y are not connected, then if Z was not in the subset U that made X and Y independent in this part for finding the skeleton, then we would make XZY a V structure. Otherwise, if this wouldn't hold, then we wouldn't do anything. And the last step was to find the orientations of the other edges by, for example, the rules R1, R2, R3. Now, this algorithm is known as the PC algorithm, and it has a nice property that if the distribution P that we're interested in has a P map, say a graph G, then this algorithm will provide that a PDAG class of G. So if the P map exists, this algorithm will find it. And of course, I'm putting aside the implementation considerations, such as how reliable from the data I can say that X and Y will be independent given U. And if this is incorrectly estimated, we incorrectly say that they're independent, what are the consequences? It has been shown that it can be misleading to the whole graph. I'm putting those aside and just theoretically, let's say under enough data, correct data, then this is possible. Now, what is the complexity order of the algorithm? Recall order of complexity. To assess the efficiency of an algorithm, we evaluate its computational time complexity, which is a measure for the algorithm runtime or the number of operations based on its input size. For example, if the input is a list, the number of the elements in that list can be the input size. If the input size is n, the computational time complexity is defined as a function fn. Finding the exact runtime is often infeasible, so we compute an upper limit for the runtime, which is called the order of complexity denoted by O. We say an algorithm is of order O of Gn and write Fn equals to O of Gn if there exists a constant C such that Fn is less than or equal to C of Gn for each input size n. Obviously, constant coefficients don't affect the order. For example, both n squared and thousands times n squared are of order O of n squared, so this 1000 doesn't matter. An important property is that the order of the sum of several functions is equal to the order of the greatest function. So for example, if I have n cubed here plus square root of n plus log of n, well, this n cube is the largest one, so the order here will be n cube. Okay, now given all this, what is the complexity order of our algorithm here? Well, it will be O of n to the power of d plus 2 if we limit the number of parents to d. So if for every variable I say that the number of parents for that variable is at most d, then the order of complexity will be n to the power of d plus 2. Okay, so I will like to conclude with another example. Let's see one with 5 variables. We start with the fully connected network here, and then we look into the conditional independencies. We start with small u here. We start with if there is no zero order independencies, u equal to 0, then I cannot remove any edges. Now imagine that the first order independencies are as follows. So then, for example, A is independent of C condition on B. So that means that I need to remove the edge between A and C. I need to remove, similarly, the edge between A and D, C and D, and A and E. Okay, so this one here. This is what I will get as the skeleton up to here. And it's saying that just assume that the second order independence is this one. B and E are independent condition on C and D. So I can remove this edge here and assume that no other edges can be removed. So this is the skeleton. Now how should I decide on the edges, on the direction of the links? Well, I see that CED here is a potential immorality, and E does not show up in the U that made C and D independent. This is evident from what we saw here. C and D became independent condition on B, not E. So here I should make this a V structure. Okay. And what about the other ones? Say ABC, ABD, CBD. All of these, you see that the one that made them conditional independent, it's B, and B is appearing here as the child, so I shouldn't touch them. I should not make any of these a V structure or an immorality. So I'm done. This is the final PDAG, and no other directions can be concluded. Okay, summary. The goal is to systematically find a class PDAG PMAP from data. How? Well, one approach is constraint-based, and how does it work? Well, we start from a fully connected network, okay, and iteratively remove edges between every pair of nodes xy that are conditionally independent given one or more of their neighbors. So here I see that M and D are conditionally independent on C, so I will remove the edge, and also C and D are conditionally independent on M, so I will remove the link between C and D, this is what I will get. And in the next step, we said that we will turn X, Y, and every non-parent neighbor into a V structure. Here, this does not happen. I only have one edge. And after that, we orient the other edges to avoid cycles and new immoralities. Okay, so I will get at the end a PDAG. Now, there is a question though. What we didn't cover in this section was how do we conclude on these conditional independencies? How from data I decide whether M and D are independent condition on C?